Now we are going to see the memory decoding, the topic of the fourth unit. So decoder. So in order to select the memory word specified by a particular input address, we need decoder. Okay. So the this is a memory cell. This is a memory cell and 1-bit memory cell. Okay. So it will be having a flip flop and it will be having an input line, then a select line, then output line and a read write line. This is a simple block diagram of a memory cell. Okay. So this is a 1-bit memory cell and it will be having a SR flip flop and it is having a select line and input output and read or write. So in the memory you know that we can perform read operation or write operation. Okay. This is a 1-bit memory cell. Now, so here you are having n rows. To the n rows, the memory cells are connected. Okay. So the number of cells grouped together and to form a memory unit. And this is an individual memory cell. And this is nothing but data input output. Okay. So here the output is having a word length of 4. Now, this diagram is nothing but the diagram of a uh, uh, diagram of a 4 into 16 decoder. So this it is having 4 inputs and it is having 16 outputs. Okay. So these 16 output lines you have connected the memory cells. Okay. So we have connected the memory cells and the output is having a word length of 8. So you are having 8 outputs B0 to B7 and it is having a word length of 8 and this is nothing but a 4 to 16 decoder. So the 4 input, so um, 2 to the power 4 is 16. So this 4 inputs can give 16 different addresses. Okay. So this is a address decoder, 4 into 16 address decoder. And already I have told you that it is having input, output, then read and write line. Okay. These are the things what you're having in your memory. Now from the organization, that the previous diagram is nothing but the organization of memory. From the organization of memory, there is a need for decoding circuit to select the memory word specified by the memory address. So in order to select the particular memory word from that memory, we need an address. Okay. So we need a decoder. That decoder will decode that particular address and it will take the particular information from the memory. The previous figure is nothing but the figure of 4 into 16 decoder. A memory with 16 words need 4 address lines. So it is having 4 input. That 4 input is nothing but the 4 address lines. Okay. So it is having 16 outputs. 4 address input go through the 4 into 16 decoder to select one of the 16 words. So at a time we can select one of the 16 words. The decoder is enabled with the memory enabled input. When the enabled input is 1, then the decoder is enabled. When the memory enable is 0, all the output of the decoder is 0 and none of the memory words are selected. So your memory enable is 0, nothing will happen and the particular decoder will be not working. With the memory select at 1, one of the 16 word is selected, detected the value in the 4 address lines. So depending upon the input value what you are giving in the input, one of the 16 words that is selected. One of the 16 address will be selected. Once the word has been selected, the read and write input determines the operation. So we will be giving the input, that input determines the address. After that, the either read operation can be done or write operation can be done. So if read operation is done, then the particular information will be retrieved from the memory. If write operation has to be done, some data will be written into the memory. During the write operation, the data available in the input lines are transferred into the 8 memory cells of the selected word. So the memory cells that are not selected are disabled and their previous binary value remains unchanged. So while giving an input address, only a particular memory cells are selected, and the memory cells that are not selected are disabled and the previous binary value remain unchanged. What value it is previously present in that particular cells, it will be present there. Now, next we are going for coincident decoding. So it is a two-dimensional selection scheme. So a decoder with k input and 2 to the power k output requires 2 to the power k AND gates and k input per gate. Okay. A decoder with k input and 2 to the power k output requires 2 to the power k AND gates with k input per gate. A k input decoder can be implemented with two k by 2 input decoders and one for column and another for row. So how we are doing is, instead of going for one decoder, we are doing it by two decoders. A two-dimensional coincident decoding is more efficient decoding scheme for larger memories. So for larger memories, this coincident decoding is very important and it will be very useful for large memories. So how we are implementing is, if you are having k input decoder, that same decoder we are implementing by 2 k by 2 input decoder. Sorry, one for row and another one for column. Example, a 10 into 1024 decoder can be implemented by using two 5 into 32 decoders. So one example we are taking, we are considering a 10 cross 1024 decoder that we are implementing by using two 5 into 32 decoders. So this is an example. So this is a 5 into 32 decoder and this is a 5 into 32 decoder. This is for row and this is for column. So with a single decoder, we need 1024 gates with the 10 inputs each. Okay. So 2 to the power 10 is 1024. So we need 10 inputs each. But in the case of two decoder, we need only 64 gate with 5 input each. The 5 most significant bit of address goes to input A and 5 LSB of the address goes to B. Here the 5 most significant bit of address goes to A and 5 least significant bit goes to B. So here I will show. Here the 5 most significant bit goes to this A and the 5 least significant bits go to B, that is X and Y. Each word in the memory array is selected by the coincidence of A and B. So it is selected by the coincidence of A and B or X or Y. Thus, each word in the memory is selected by the coincidence between one of 32 rows and one of 32 columns for a total of 1024 words. So each word in the memory is selected by the coincidence of between one of 32 rows and one of 32 columns. So of this, we have completed our memory decoding. So what is decoding? So in the address decoder will be having inputs. That inputs will be if it is having n inputs, it will be giving 2 to the power n address. So in order to get the specific address to select the particular memory, you are using this memory decoding. So today we are going to see the topic programmable logic devices. This is a topic in the fourth unit. We are going to see programmable logic devices. Okay. Now, what is programmable logic devices? So before going into programmable logic devices, we must understand what is meant by logic devices. A logic device is an electronic component which performs a definite function which is decided at the time of manufacture and will never change. Okay, so will perform a definite function, and it is which is decided at the time of manufacture, and it will never change. This word never changes important. So in logic device we can't change, uh, we can't change what we can't change the function. So it will perform some definite function, and that function is decided at the time of manufacture, and after manufacture we can't change that. That is nothing but logic device. Now we'll come to programmable logic devices. Programmable logic devices are components which do not have specific function associated with them. So it is a general device and it will not have any specific function, do not have any specific function associated with them. These can be configured to perform a certain function by the user. The user can configure this for a specific function. So we can the user can configure this circuit for a specific function on need basis, and can be further changed to perform some other function at later point. Okay, so it is a reconfigurable one. This programmable logic devices is a reconfigurable one. Okay, now the types of programmable logic device are ROM, programmable logic array, and programmable array logic. So ROM is read-only memory. This read-only memory, this programmable logic array, and programmable array logic. These three are the types of. There are also many types, but we are studying only these three types. That is ROM, programmable logic array, and programmable array logic. These are the three types of programmable logic devices that we are going to study in this fourth unit. Okay, now we will come to ROM. ROM is nothing but read-only memory. Already we have seen that it is a non-volatile memory, and in this read-only memory is a memory device which permanent binary information can be stored. Okay, so in ROM you can store permanent binary information. Okay, even if the power is gone, the memory will be there. So we can use for a permanent information storage. Then this is a block diagram of ROM. So it is having k inputs and it is having n outputs, and usually we will be representing the ROM by 2 to the power k into n. This ROM will be having decoder and OR gates. The ROM includes a decoder and a all gates. These two things will be having in a ROM IC package. Okay, in a ROM IC package, you will be having decoder and OR gates. The number of words in a ROM is determined by the K address input lines. So the number of words is determined by the K input address. Lines need to specify that 2 to the power k words. Okay. So the number of words in a ROM is determined by the k address input lines that is needed to specify 2 to the power k words. So ROM consists of k inputs and m outputs. Each bit combination of input is called an address. Okay. So already I have told you that it is having k inputs and m outputs, and each bit combination of input is called, we'll be calling it an address, and each bit combination that comes out of the output line is called a word. So the input bit combination we will be calling as address, and output bit combination we will be calling it as word. Okay, so in a ROM the input bit combination we will be calling it as address, and the output bit combination what we are getting is nothing but word. Next, the ROM does not have data inputs because it does not have write operation. This word is important. In ROM, we can do only read operation, and write operation is not permitted. So it does not have data inputs. So this ROM does not have data inputs. The number of bits per word is equal to the number of output lines. So number of bits per word is equal to number of output lines. If you are having 5 output lines, then the number of bit per word is 5. Okay. An address is essentially a binary number that denotes one of the minterms of k variables. So already we see that the input bit combination, it is nothing called the address. This address is a binary number that denotes one of the minterms of k variables. Okay, so it is a minterm of k variable, one of the minterm of k variables, because in input of ROM we considered that we will be having k inputs. So that address is nothing but it is a binary number that denotes a minterm of the k variables. With the k variable we will be having 2 to the power k distinct address. Already I have told you, if you are having n variable we will be having 2 to the power n combination. Since we are having k inputs, we will be having 2 to the power k distinct address. Now an output word can be selected by a unique address. Okay, so the address are unique and a particular output word will be having a unique address. So each output will be having a unique address. So by selecting that unique address, we can get that particular word from the memory. The word available at the output line at a given time depends upon the address value applied to the input line. Okay, so the word available at the output depends upon the what address you are giving at that time. So if you use some particular address, the data from that particular address will be retrieved and it will be coming to the output. ROM is a two-level implementation in SOP, sum of minterm form. So what is ROM? ROM is a two-level implementation in sum of minterm form. Okay. Now internal logic of a 32 into 8 ROM. Already I have told you that ROM will be having decoder and OR gates. So this 32 indicates 2 to the power 5 is 32 into 8. The 32 can be written as 2 to the power 5 into 8. This 5 represents the input of the decoder. If a decoder is having 5 inputs, then it will be having 32 outputs, 0 to 31. Okay. So if it is having 5 inputs, then it will be having 32 outputs. This 8 represents the number of words in the output word. It is having 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So you'll be having 8 OR gates and you'll be having a 5 to 32 decoder. Okay, we'll be having a 5 to 32 decoder. So this is nothing but the internal logic of a 32 into 8 ROM. This 32 we can write it as 2 to the power 5 into 8. So this 5 is nothing but input address and 8 is nothing but bit number of output word. Okay. Now we are going for the programming the ROM. So how to program a ROM. So already we have studied the internal structure of a file that 32 into 8 ROM. So I will here we are going for the programming. So in this programmable logic devices, programming is nothing but doing the phase is called programming. So here in some places there is a small marking, X marking. This X denote the connection in the place of a dot used it for a permanent connection. Okay, denote a connection in a place of a dot. This X means we have programmed. So the meaning of this is this A7 is having a value of 0, 2, 3, 29. So these minterms are present in A7. Similarly for A6, the minterm 2, 29 and 30 are present. Similarly, A5, you're having 0, 3, 29, and 31. So these minterms, the 0, 1, 0, 3, 29, and 31, these minterms are true for this gate A5. This or gate A5. This is nothing but programming. Okay, programming in Rome is nothing but it is nothing but blowing the fuse. We'll be calling it as programming. So programming is nothing but a reconfiguring. Initially, it is not having any. I will explain clearly. Initially, it is not having any proper function. After after getting into the user depending upon his or her wish, they will be reconfiguring the circuit for their particular application. So this is nothing but programming is nothing but reconfiguring. Simple, we can say it as reconfiguring according to our need is nothing called reconfiguring of programmable logic devices. Initially, it is not having any definite function. Now we will be changing that circuit according to our function. Okay, depending upon our function and our need, we will be reprogramming it. Okay, or we will be reconfiguring it. So in Rome, you'll be having a Rome truth table. This Rome truth table will be having inputs and outputs. So this it will shows for which particular set of inputs, which particular set of output will be having a high value. From this only we are programming that. Initially, we have seen that this diagram. In some places, they will be having some cross. It is nothing but reconfiguring. So according to this truth table will be only we have reconfigured that row. So we will put one in the cross in the place of 0, and we will be putting cross in the place of 2, 3, then similarly 29, etc. For A7, similarly for A0, A1, and A2. So we have reconfigured it depending upon this row truth table only. So first, depending upon your problem, if you are having some problem or some circuit, you will be having a truth table. From the truth table, you will be reconfiguring your ROM. So this is the so so here you are having a 5 that is 32 into 8 row, and it will be having 256 programmable interconnections. These each one is nothing but programmable interconnections. The connection point of each row and each column is nothing but a cross point. So here you will be having 256 programmable interconnections. Okay, so 31 32 0 to 32 into 8. Okay, so you will be having 256 programmable interconnections. Here you will be having now programmable connection or a cross point between two lines is logically equal to a switch. This connection is equal to a switch which can be opened or closed. A switch can be a fuse that normally connects the 2 points but can be opened by blowing the fuse using a high voltage. Usually it will be a fuse. The switch will be in the form of fuse, and initially it will be closed. If you want, you can blow the fuse by applying high voltage to that particular point. Okay, so this is the programming here is blowing the fuse. Okay, in this programmable logic devices, programming means blowing the fuse or reconfiguring. Now we are going to see one problem in Rome. So implement the following Boolean function using Rome. So what they are saying, they are asking us to implement a Boolean function using Rome. Okay. Now these are the question. F1 of A1 A0 is equal to summation of M1 2. Then F2, this is not F1, F2. F2 of A1 A0 is equal to summation of M0 1 3. So totally they are giving two functions. So F1, F2 are the two functions, and A1, A0 are the A1, A0 are the inputs, two inputs. You are having two inputs and two outputs. So inputs, you write it as 2 to the power 2 into 2. So you need a 4 into 1 row. To implement this, you need a 4 into 1 row. Then one important thing I am telling, in Rome, there is no need of minimization. So next we are going for PAL as well as PLA. In those two, we have to go for minimization. But you should remember that in Rome, there is no need of minimization. So first point is, from the given question, we must understand by using which Rome we have to implement. So here, how many input variables you are having? Two input variables, A1 and A0. So K is equal to 2. How many output variable? 2. M is equal to 2. So you have to go for a 2 to the power K, actually 2 to the power K into M. So 2 to the 4 in, that is 4 to 4 into 2 Rome you have to go. So from the question, we understand that you have to go for 4 to 1 Rome. First is, we have drawn the 4 is to 2 to the 4. So we know that we need a 4 into 2 Rome. But Rome consists of what? Rome consists of decoder and OR gates. So 2 to the power 2. So you need a 2 to 4 decoder. So, and you need two OR gates. So what are the things you need? You need you need first you need 2 to 4 decoder. So this is a general representation of a ROM 2 to the power k into m. So this m represents the number of OR gates. So two OR gates. So 2 to the power k. This k is nothing but the input of decoder, and 2 to the power k is nothing but the output of decoder. So first you need a 2 to 4 decoder. Okay. So we have drawn a 2 to 4 decoder. So to that 2 to 4 decoder, we have connected two OR gates. Now we are this is nothing but the diagram. 4 is to 2 Rome. This is nothing but 4 into 4 cross 2 Rome. Now we have to program. So this is F1 and this is F2. This is F1 and this is F2. Now we are going for programming. Programming means these are the interconnections or cross points. So you have to put a you have to blow the fuse for the corresponding number digits given in the question. So what are the things given in the question? F1 is equal to 1 2. F1 is equal to 1 2. So you have to put 1 2. For F2 0 1 3. 0 1 3. So this is nothing called programming. So in the next figure, you will be clearly understanding. So this is nothing but programming. So we have implemented the given Boolean function by using Rome. So here the important thing what you have to remember is, here there is no need for simplification of Boolean function by using Rome. Next problem. Design a combinational circuit using Rome. Okay, they have given that you have to design a combinational circuit using Rome. The circuit accepts 3-bit binary number. So what is the input of a the circuit accepts 3-bit binary number. What number it is accepting? It is accepting a 3-bit binary number and generates its equivalent XS3. So what is the output? Its output is nothing but an XS3. So it is accepting a 3-bit number. So first we have to write the 3-bit number from 0 to 7. Then what is the XS3 of 7? 7 plus 3 is 10. So 1010 is 10. So you need 3 variables for input and you need 4 variables for output. Okay. The next I will show what is. So this is nothing but the truth table of binary to the question what they are given is it will be getting an input as binary and it will be giving the output as XS3. Okay, so the input is nothing but a 3-bit number. So we have to write from 0 to 111. So you know that if you are having 3-bit, you will be having 8 combinations, that is from 0 to 7. So in binary using 4 to 1, you have to write from 0 to 7. Already we have studied all these things, but again I am telling. So by this way you have to write from 0 to 7. Then what is the XS3 of 0? It is 3. 0, 0, 1, 1. What is the XS3 of 1? It is 4. What is the XS3 of 2? 5. What is the XS3 of 3? 6. What is the XS3 of 4? 7. What is the XS3 of 5? 8. XS3 of 6? 9. XS3 of 7? 10. So we have written the input and output and we have completed the truth table. Okay. We have completed the truth table. Or it can be taken as a ROM truth table also. Okay. Our own programming table. So next we are going for implementation. So how many input you are having? So here next step is we have to find the proper ROM to implement. So how many inputs you are having? 3 inputs. 3 inputs means 2 to the power 3. How many outputs it is having? 4. So you need a 8 cross 4 ROM. So what do you need? We need a 8 cross ROM to implement. But ROM consists of a decoder and OR gates. So you need a 2 to the power 3 is 8. So 3 to 8 decoder. How much decoder you need? 3 to 8 decoder and you need 4 OR gates. You need 4 OR gates and 3 to 8 decoder. What are the things you need? You need a 3 to 8 decoder. You need a 3 to 8 decoder. You need a 3 to 8 decoder and 4 OR gates, 4 OR gates to implement this problem. Okay, so so these 3 inputs you take it as A, B, and C. This A1, A1, A2, A0, A1, A2 is nothing but A, B, C. So 3 to 8 decoder will be having 3 inputs and 8 outputs. And since we are having our problem is having 4 outputs, we have drawn 4 OR gates. Then by looking the column of E naught, for which are the numbers we will check. For E naught 5, 6, 7. So for E naught 5, 6, 7 or 1. So we have blowed the fuse at 5, 6 and 7. Similarly for E2 1, 2, 3, 4. Similarly by checking the column of this is for E3, this is for E2 and this is for E1. While checking the column of E1, we have got that we are having 1 in the place of 0, 3, 4 and 7. And we have blown the fuse in the place of, or we have, the particular cross points, we have blown the fuse and we have programmed. Similarly for E0, we are having 1 in the place of 0, 2, 4 and 6. And we have blown the particular fuses and we have implemented the circuit by using ROM. Okay, main thing is first you have to, if some problem is given, first you have to find the truth, first you have to write the truth table. Then from the truth table you have to find the appropriate ROM. So the next step is to find the number of OR gates and number of the proper decoder. The number of OR gates depends upon the number of outputs you are having, and the decoder depends upon the number of inputs you are having. So from that we have got that. Next, we are going again for another problem. We are going to design a combinational circuit with three input. How many input you are having? Three input. Then output of the circuit is nothing but square of the input. So what is output? Output of the circuit is square of the input. So we have to design a circuit which should accept a three bit input, and it would generates the output. That output should be nothing but the square of the input. So similar to the previous problem, since we are having three input, we have to write from 0 to 7. So what is the output of the circuit? Output of the circuit is nothing but the square of the input. What is the 0 square? 0 square is 0. Similarly, what is the square of 7? 7 is nothing but 49. To represent 49, you need 6 bits. So minimum you need, maximum you can have many bits, but minimum to represent 49, you need 6 bits. So in output, we need 6. Okay, 6 variables to represent the output, and input we need 3. Okay, then we are going to write the truth table for this circuit or this problem. So input is nothing but the 3-bit number. So we are writing from 0 to 7. Then we are writing the square of the number in 6 bits. Why? Because the largest number here is 7. The 7 square is 49. To represent 49, you need 6 bits. So we are writing all the numbers in 6 bits. So the 0 square is 0, 1 square is 1, 2 square is 4, then 3 square is 9, 4 square is 16, 5 square 25, 6 square 36, and 7 square 49. So we have written the binary values of these squares. This is nothing but the decimal value. Then we have written the binary values using 6 bits. So you are having 3 inputs and 6 outputs. Okay. Now this is a particular problem. In this problem, we have to be careful in doing this problem. Now you check A naught and B naught, they are same. A naught and B naught are same. And similarly, B1, all the numbers are 0. So A naught and B naught are same, and B1 is 0. So in particular problem, instead of taking 6 OR gates, we are taking only 4 OR gates. I will tell. Oh, so this problem is implemented in another way. So how many inputs you are having? Actually, 3 inputs. And how many outputs you are having? Actually, 6 outputs. Out of that 6 outputs, one output is similar to A naught, and another output is 0, and we are neglecting that two outputs. So 4. Now, since you are having 3 inputs, you need a 3 to 8 decoder. So you need a 3 to 8 decoder. But in the case of OR gates, you need only 4 OR gates and not 6, because we can directly take one line from A naught and we can give it as B naught. Why? Because A naught and B naught are same. Similarly, B1. B1 is all 0, so we can ground it. So this is an implementation. So you can implement the same circuit by using 3 to 8 decoder and 4 uh, OR gates. Okay. So then after checking the particular column of that B3, B0, B1, B3, B2, B1, then you can you can program the particular cross points. Okay. So this is a block diagram representation of the problem. You can do it by ordinary 3 to 8 decoder and 4 OR gates, but don't take as 6 OR gates, because the two of the outputs, one is similar to A naught and another one is full 0. So there is no need to go for another 2 OR gates. So you implement this question by using only. Next, we are going to see the advantages of ROM. Since no minimization of logic function is required, it is easy to design. So while doing the problems and all, we see that well, we have not gone for any Boolean function reduction. So we have directly implemented. So it is very easy to design. Then design can be modified easily. So modification of the design also very easy. So it is faster than small scale integration and medium scale integration circuit. Okay. This ROM is more faster than small scale integration and medium scale integration circuits. Now we are going for the disadvantage. So all the bit patterns available in the ROM is not used. When combinational circuit is having any don't care, when the combinational circuit is having any don't care, so the all the bit pattern available in the ROM is not used. Or if the combinational circuit is not having all the min terms, then also the all the bit patterns is not used in the ROM. So it is a wastage of available equipment. So this is a disadvantage, and another disadvantage is it will require more power, and the size of this ROM is it is having an increased size. So the main disadvantage is all the bit patterns of the ROM are not used if it is having don't cares. Okay, so it is an wastage of the available equipment, and it requires more power, and the size of the ROM is very large. So these are the disadvantages of a ROM. So to overcome these disadvantages, we are going for, so before going that, we are going for the PLA. Now we are going to see the type of ROMs. First one, mask programming ROM or mask ROM. So, so it is done by the fabrication company during the last fabrication. That is, programming is done by the company only. The user can't do anything. He can give the truth table. By looking upon the truth table, the company will be doing all the things. Okay. So the last fabrication step, they will be doing all the thing. So the cost of this mask ROM is very high. Next we are going for programmable read only memory, that is PROM. So it allows the users to program in the lab. So this programmable read only memory or PROM, it allows the users to program in lab. So the program is irreversible. Okay, so you can reverse it. Now we are going for erasable programmable ROM. So initially we have seen PROM, now we are seeing EEPROM. So here erasing job is done by ultraviolet. By passing ultraviolet rays, we can erase the programs. Next one is electrically erasable PROM or E square PROM. So here by providing electrical signal, we can erase. Okay. So it can be erased without removing from the socket. Now we are going for PLA. So PLA is nothing but programmable logic array. So PLA is programmable logic array. So this programmable logic array will be having n inputs, m outputs, and k product terms and m sum terms. So what are the things you'll be having? This P This PLA will be having n inputs, it will be having m outputs, k product terms, and m sum terms. In PLA, we'll be having AND gates and OR gates, and this both OR gates as well as AND gates are programmable. So in PLA, both AND gates and OR gates are programmable. This PLA is more flexible. It will be having n inputs, m outputs, k product term, and m sum term. The PLA consists of k AND gates which can be programmed to generate the product terms. So it will be having k AND gates, and this AND gates can be used to program the product terms. Then it will be having k AND gates, and it will be also having m OR gates which can be programmed to get sum of products. Okay, so for product terms, AND gates can be programmed. In order to get SOP, we can program this OR gates. So in PLA, both the AND gates as well as OR gates are programmable. The output can be generated either in and or form or and or invert form. Okay, so the output can be an and or form or and or invert form. If the fuse in the output is disconnected, we will get and or invert form. If the inverter in the output is bypassed by the link, then and or form is obtained. Okay, there are two forms, and or form and or invert form. Okay, if you bypass the fuse, then you'll be getting and or form. Okay, if you disconnect, then you'll be getting and or invert form. Now we are going for the block diagram of the we are going for the block diagram of PLA. PLA is programmable logic array. Programmable logic array. Okay, logic array. Okay, now here it is having K product terms, M sum terms, okay, and it is having N inputs and M outputs. So, so this is a block diagram. So this is to get and or form or and or invert form. Okay, so if you bypass this fuse, if you bypass this fuse, then you'll be getting and or invert. Okay, so if not, you'll be getting and or form. So this is a block diagram of your PLA, programmable logic array. Now this is a diagram of PLA having three inputs, four product terms, and two outputs. So this is a diagram of a PLA having three inputs. This particular problem is having three inputs, four product terms, and two outputs. The three inputs are A, B, C. So here you are having an inverter buffer. From this inverter buffer, you will be getting the true form of the variable and complement form. So this is A, so you are getting A and A bar. This is B, you are getting B and B bar. This is C, you are getting C and C bar. And it is having four AND gates. So the product terms can be implemented by using AND gates, and SOP it can be implemented by using OR gates. So the function of this F1 and F2. So it is to get the and or invert and or invert. So we know that if you are giving one of the input of the XOR gate, then the output is nothing but the complement of the input. Similarly, if you give 0 to the one of the input of XOR gate, then the output will be equal to the other input. So by using this, you are you can get the complement of the function or the true form of the function. This is the use of this XOR gate. The use of this XOR gate is to get either the true form or complement form of the function. Okay, so here this is an PLA with the three inputs, four product terms, and two outputs. Whatever may be the problem, we can do it by using this PLA. So in the second unit we have studied the design of combinational circuit. So the code converters and many circuits we have studied. So we can implement all those circuits by using PLA. Sometimes problems may come. Design a BCD to XS3 code converter using PLA. So all the things are same except that last diagram. So up to that getting the K map and expression you have to do, and then after that you have to count how many product terms you are having in your problem, and then you have to draw as much AND gates. Then you check how many outputs you are having. Then you have to draw as much OR gates. Then you have to do the problem. It is very easy by doing the problem in PLA. Okay, so PLA is programmable logic array, and here you are having AND gates and OR gates. Here both the AND gates and OR gates are programmable, and it is having more flexibility. Okay, it is more flexibility. It is having, and it is having more advantages than that of Rome. And most of the disadvantage of Rome we are overcoming in this PLA. Okay, now we are going for a problem. So the next we are going to study PLA programming table. So what does mean by PLA programming table? This PLA programming table will be having the three things. First, the list of product terms. Next, we will be having, you have to specify the required path between input and output. And third specifies the path between and OR gates. So the PLA programming table will be having three important information. First one is, it will be, first we have to list the number of product terms. Then we have to specify the required path between inputs and the AND gates. Then we have to specify the path between AND gate and OR gate. These are the three things what the PLA programming table will be having. Now we are going to implement the following Boolean function using three inputs, four product terms and two outputs. So we are going for a problem. So they are going to they are telling is, we have to design, or you have to implement a Boolean function using PLA, which is having three inputs, four product terms and two outputs. So they have given the two functions, that is f1 of ABC is equal to 0, 1, 2, 4, and f2 of ABC is equal to 0, 5, 6, 7. So similar to the uh, um, so here what you have to do means, it is entirely different from that of Rome. Here the first step what you have to do is, you have to go for minimization of Boolean function. But in the case of Rome, we are not going for any minimization. But in PLA and PAL, the first step what we have to do is, we have to go for minimization. Here we are having two functions, f1 and f2, and we are having three inputs, A and B. So from the question we have understand two things. The two things are, the not two things, we have understand three things. One is, we are having two functions, f1 and f2, and the functions, the two functions, they are having three inputs, A and B, and the given functions are in SOP. Okay, these are the things what you understand from this um, question. Moreover, they are saying we must do the problem by using three inputs and four product terms and two outputs. We should not exceed this four product terms and two outputs. Okay, the product term should not exceed four. So we must take special care to do the problem by only using four product term. So if any case, if you are getting more than four product term, so we have to check for some alternative to bring that into four product terms. Okay, so the first step what you are doing, we have to do is, we have to minimize this function using kmap. So this function is having three variables, so A, B, C, and it is having we are having two functions. So we have to draw two three variable k-map, one for f1 and another one for f2. So what we have to do? We have to do, first step is, we have to draw two k-maps for one for f1 and another for f2. The variables of k-maps are A, B and C, because we are here we are having three variables A, B, C. So, and the minterms for f1 is 0, 1, 2, 4, and the minterms for f2 is 0, 5, 6, 7. So we have to put 1 in the place of 0, 1, 2, 4 in the k-map for f1, and we have to put 1 in the place of 0, 5, 6, 7 in the k-map of f2. Okay, so this is the first step what we have to do. So after doing this, now we are going for the simplification by using k-map. So this is nothing but the k-map of f1. This is a k-map of f1, the function f1. Now we have plotted the min terms of f1. F1 is 0, 1, 2 and 4. The given numbers we have plotted. Now after plotting we are going for grouping. So here we can group these two ones and this one. These are the three grouping what you can done, and the expression is for, so this is the grouping for your K map, and here you are having three pairs, and this first vertical pair your expression is B bar C bar, and for first horizontal this red color, that is expression is A bar B bar, and for this blue it is A bar C bar. So the expression is F1 is equal to A bar C bar, A bar B bar, B bar C bar. This is a K map for K1, and while getting that minimizing we are getting three terms. These three terms indicates three product terms. The three terms are nothing but three product term. This is a product term, this is a product term, and this is a product terms. Totally we got three product terms. Similarly, we are going to draw the K map for F2. So initially we have written it for F1. Now we are going it for F2. Now here you are having two pairs and an individual one. So we have to write the expression. So expression for this first horizontal pair is AC. So first one is AC, and second one is AB, and for this one is A bar B bar C bar. A bar B bar C bar. So totally you are having three terms. Now so here the term is here the terms are three product terms. A bar B bar C one product term, AC another product term, AB another product term. So now you have to check the product terms of both F1 and F2. We have found the expressions for F1 and F2. Now we have to compare. So the two expressions. So A bar C bar one product term. Okay, do you have any similar product term in F2? No. A bar B bar second product term. Do you have any similar product terms in F2? If similar product terms are there, so for those two we have to consider only one. So next one B bar C bar third product term. Do you have any similar product term in F2? No. So next one A bar B bar C bar. This is fourth product term. Next one AC fifth product term, and next one AP sixth product term. So totally by getting the expression or by minimizing the K-map of the function F1 and F2, we are getting six product terms. But in the question, they are asked us to do the problem by four product terms. How many product terms they are telling? They are telling us to implement this problem by only four product term, but while taking or while getting the expression or minimizing that boolean function f1 and f2, we are getting six product term. So next what we have to do is we have to take the complement of f1 and we have to take the complement of f2. So complement this is a k map for F1. That is nothing but in F1, wherever you are not having 1. So actually, we have plotted one K-map for F1. So in that F1, wherever you are not having 1, in that places you have to put 1 in F1 bar. This is a K-map for F1 bar. F1 bar. Okay. So for that, what we have to do is in the places where you are not having 1 in F1 map, the K map of F1, wherever you are not having 1, you have to uh, plot once. Okay, you have to plot once in the K map where you are not having 1 in F1. So this is F1 bar. So for example, I will tell. Please listen. This is a K map for F1 and this is a K map for F1 bar. So in order to get to plot the K map for F1 bar, what you have to do means you have to plot 1 in the place where you are not having 1 in. This is a K map of F1. So here you are not having 1. So in the F1 bar map, you have to put a 1. Here you are not having 1 in F1 map. So you have to put 1 in the place of F1 bar map. Similarly, here you are not having 1 in the place of F1 map. So you have to put 1 in the F1 bar map. Similarly, here you are not having 1 in the place of F1 map. So you have to put 1 in the place of F1 bar map. Okay. So we get the F1 bar map. Okay. Now we got F1 bar map. So from this F1 bar map, you are getting the expression. That expression is BC plus A. So I will tell the expression. The expression is nothing but what you are getting is you are having 3 groups. The expression is AC plus AB plus BC. So 3 product terms you are getting. Okay, what is the product terms? AC plus AB plus BC. So you are having this for this one. This is BC. For this one, it is AC, and for this blue it is AB. So 3 product terms you have got. Similarly, you have to go for F2 bar. So F2 bar is nothing but you have to put 1 in the places where you are not having 1 in the place of F2 map. Okay. So how you will be getting F2 bar map? F2 bar map is obtained by putting 1 in the place where you are not having 1 in the place of place in F2. First you have to take the F2 map. In F2 map, the certain cells will be empty. So without ones. In the F2 bar map, in those cells we have to put 1. So in for F1 I have clearly shown. Okay. Similarly, you have to plot and you have to get the expression for F2 bar. So we have initially found out F1 and F2. Now we have found out F1 bar and F2 bar. Okay. Now we are going to compare. We are going to compare either. So now we are having 4 expression. That is nothing but you're having F1, F2, F1 bar, F2 bar. So initially we have compared F1 and F2. So we have compared F1 and F2 and totally we got 6 product terms. And now our next step is to compare F1 and F2 bar. So we are comparing F1 and. So first we have compared F1 and F2. After comparing, we have got how many product terms? 6 product terms we have got. So we can't implement because in the question they have used, they have clearly mentioned we have to do it by 4 product terms. So then we are going to compare F1 bar and F2. We are going to compare F1 bar and F2. Here you are having AC. So the same term is present here. Okay. So 1. Then AB. The same is present in F2. So 2, BC 3, and here 4. So we got 4 product terms. So we can implement. So but we can check that F1 and F2 bar also. So here A bar, C bar. Do you have any A bar, C bar in no, 1. A bar, B bar, 2. B bar, C bar, 3. A, B bar, C bar, 4. Then 5, 6. So when considering F1 and F2 bar also, we are getting 6 product terms. So only by taking F1 bar and F2, we can we are getting only 4 product terms, and so we have to consider F1 bar and F2. So for first we have how we, how we have arrived at this step. First we have got the we drawn the K map, then got the expression for F1, then we drawn the K map for F2 and got the expression for F2. Then we have checked the expressions for F1 and F2, but the number of product term is greater than 4. Then we have take the complement F1 bar and F2 bar. Then we have compared F1 with F1 bar with the F2 and F1 with the F2 bar, and finally we come into a conclusion that by considering F1 bar and F2, and we can implement this question. Okay, now F1 bar and F2, like taking these two, we are getting only 4 product terms. Sorry, not. So this is a programming table for this is a programming table for PLA. This is called PLA programming table. So it is having product terms. So product terms is totally we are having 4 product terms. The 4 product terms we have written. Then we have written the inputs. Okay, 3 inputs we are having. Then the outputs, 2 outputs, F1 and F2. Okay, first we have written the product terms. Then we have written the variables A, B, and C. The first product term is AB. So we are putting 1 in the place of A and 1 in the place of B, and the variable C is missing. So he put a small dash, and this AB is present in both the function F1 and F2. So we have put 1 in the place of F1 and F2. Output, we are having 2 outputs, and this AB is present in both the F1 and F2. Similarly, AC, we have put 1 in the place of A, and this AC also we are putting 1 in the place of A, and B is missing, so we have put a dash, and we have put 1 in the place of C. This term AC is also present in the expression F1 and F2. Then we are coming to BC. So the variable A is missing, so we have put a dash in the place of A, and we put 1 in the place of B and 1 in the place of C, and this term BC is present only in F2, so we are putting 1 in the place of F2 and in the dash in the place of F1. Now the last term is A bar, B bar, C bar. So since it is bar, you have to put 0 in the place of A, 0 in the place of B, and 0 in the place of C. So the product term what you are having is A bar, B bar, C bar. So we are putting 0 in the place of A, 0 in the place of B, and 0 in the place of C. It is present only in F1, and we have put 1 in the place of F1 and put a dash in F2. And in this F1, we have taken F1 bar. So we have put complement here. In F2, we have not done any modification. So we are writing it as true form. So in order to get 4 product terms, we have taken F1 bar. That is complement of F1 we have taken. So we are putting a C below this column F1. So to indicate that this F1 function is nothing but the complement function, and F2 function is a true function. So we have implemented this PLA programming table.